All right, in 7.5, we're going to be covering solving trigonometric equations. So this is going to combine what we talked about last time, which is the inverses to help us solve equations. And then we're also going to need to use identities from time to time to help us resolve an equation. So solving these equations is going to be very similar to what we did in Chapter 5, Section 5, when we had exponentials and logarithms. So if we think back to Chapter 5, we know that to undo an exponential, we used a logarithm, and to undo a logarithm, we used an exponential. Well, to undo trigonometric functions, we're going to do the same thing. We're going to use their inverse. So similarly, to get started on our first example, so step 1 would be we would need to isolate the trigonometric function. So in this case, we have 2 times the cosine of x is equal to -1. So to isolate it, we would divide both sides of the equation by 2. And then we have cosine x is equal to -1/2. So then the next step would be we need to undo the cosine. So we're going to use the inverse trigonometric function. On both sides of the equation. So by doing that, I take the cosine inverse of both sides. So cosine inverse and cosine inverse. So I have the cosine inverse of the cosine of x is equal to the cosine inverse of -1/2. So then the cosine and the cosine inverse are inverses, so they undo each other, and we're left with just x is equal to the cosine inverse of -1/2. So now we need to finish resolving this. So we think back to last time when we were talking about the inverse function. And so remember that the domain of the inverse cosine is between -1 and 1, and its range was between 0 and pi. So the cosine inverse will only ever give us one answer in between 0 and pi. So that means it's going to be in quadrant 1 or quadrant 2. So if we grab our unit circle, when we take a look at that, so quadrants 1 and 2 is the upper half of our unit circle. So remember, the cosine inverse asks us the question, what angle has the cosine of -1/2? So we know in quadrant 1 all of our trigonometric functions are positive, and we know cosine is x, so we have our x coordinate in quadrant 2 is -1/2. So then that means the angle that we are looking for is 2 pi over 3. And if we grab our graphing device and we ask it, well, what is the cosine inverse of negative 1/2? It's going to give us 2.09, but if we go 2 pi divided by 3, we get the same thing. But we have to be very, very careful when we're resolving trigonometric equations, because this did not give us all of the solutions. So let's write that down. So warning, the inverse cosine, or the inverse trig function, only gives us one angle, the angle is always in the range of the inverse function. So in this case, our range was between 0 and pi. But it turns out that we missed a solution. In fact, we missed a lot of solutions. So let's draw another picture, see what happens. So we had x equals the inverse cosine of negative 1/2, but the line before that was cosine x equals negative 1/2. So let's pull out our graphing calculator, and let's graph cosine x, and then let's graph negative 1/2. And let's press our window key. We can leave our x min and x max where they are, but let's make our y min -1, let's make our y max +1, and then let's scale in 0.1s. So we look at our cosine function, and there's negative 1/2. And as we see in this picture, we get a whole bunch of different intersection points. In fact, if we were to zoom out further in the x direction, we would get an infinite number of these. So the solution that we got above, 2 pi over 3, is this guy right here. And we'll notice that since solutions are periodic, this wave repeats itself, so our solutions are going to happen every 2 pi units. So that means I get another copy of this solution 2 pi units this way. So 2 pi over 3, take away 2 pi, which would be take away 6 pi over 3, is going to give us another solution right here at negative 4 pi over 3. And if we kept going, there would be another one here and another one here. But we'll notice our 2 pi unit spacing is still missing some solutions. So let's see why that's the case. If we go back to our unit circle, remember we were looking for outputs from the cosine function, so that's x values, where we have x is equal to 1/2. Well, x is negative in both quadrants 2 and in quadrants 3. So in our original graph here to the left, we got our one solution, which was in between 0 and pi, which was right here. But the inverse trigonometric function will always miss the solution that is in quadrant 3 or quadrant 4. So we want to note there is another solution and it's worth noting the graphing calculator will always miss this. Because the graphing calculator will only ever give us the solution between 0 and pi. So then we go down here, our other solution is going to be at x equals 4 pi over 3, which is going to be this solution right here. And then 2 pi units this way, once again, we get another solution. So we do get another solution here, and then all the 2 pi periods. So the equation has an infinite number of solutions, and they are x equals, and our first one we got up here was 2 pi over 3 plus 2 pi n for any integer. And remember, this is the set of all coterminal angles. And then we had another solution of the form x equals 4 pi over 3 plus 2 pi n, where that is our all coterminal angles again. So then that would be our complete solution for every n in the set of integers. So when resolving trigonometric equations, we have to be a little bit careful, and we need to be aware of the range of the inverse function that we're using. So when we're using the calculator, we will always get one of the 2 possible solutions, and it will give us the one in the range of that function. So since we were using cosine this time, the range was from 0 to pi. So it was going to give us the solution in either quadrant 1 or quadrant 2. But then it missed the solutions in quadrants 3 or 4 because these are not in the range of the inverse function. So these ones have to be found manually using either some reasoning and drawing reference triangles or using the unit circle. And we'll do examples of both of those as we go through solving. We'll also see some examples later on where sometimes they restrict the domain of the equation so we won't end up with these infinite sets. And we'll see some of those examples later on as well. All right, so let's take a look at example number 2. So once again, same instructions. So we want to resolve this equation. So solve 4 times sine squared x is equal to 1. So this is a quadratic trigonometric polynomial. So thinking back to chapter 3, when we resolved quadratic equations, we really had three choices. We can factor, we can use the square root principle, or we can use the quadratic equation. In this case, I'm going to just do a substitution to let me factor it. So if I let y equal sine x, then this equation becomes 4 y squared equals 1. So then I can minus 1, I minus 1, and that gives me 4y squared minus 1 equals 0. And then that's the difference of squares, so it's going to factor into 2y minus 1 times 2y plus 1 is equal to 0. And then by the zero product rule, I get 2y minus 1 equals 0, or 2y plus 1 equals 0. So then I add 1, I add 1. I get 2y equals 1, divide by 2, divide by 2. Y is equal to a half. I minus 1, I minus 1. I get 2y equals negative 1, divide by 2, divide by 2. And we get y is equal to negative 1 half. But we had that y is the same as sine x. So then what we really have are the two equations. Sine x equals plus or minus 1 half. So positive 1 half, and sine x equals negative 1 half. So now we need to solve each of these by using our inverse function. So if we take the inverse of both sides, we're going to have the sine inverse and the sine inverse. And we're going to have sine inverse and sine inverse. So we get the sine inverse of the sine of x equals sine inverse of 1 half. And sine inverse of sine x equals negative 1 half. So the sine and the sine inverse reduce out, and we get x is equal to the sine inverse of 1 half. And we get x is equal to the sine inverse of negative 1 half. So if we think back to last time, the range of the sine inverse function is negative pi over 2 to positive pi over 2. So that means the sine inverse function is only going to give us solutions in quadrant 1 and in quadrant 4. That means it is going to miss the solutions in quadrant 2 and quadrant 3. So if we grab our unit circle, the first one, the inverse sine of 1 half, is going to be in quadrant 1, which means the solution that it misses is going to be in quadrant 2. So we look at our function here. And sine is y, so we need a y value of 1 half. So that gives us this. So our solution is going to be pi over 6. The solution that it misses, we also have a y value of 1 half over here in quadrant 2. So the solution that it misses is 5 pi over 6. So the two solutions are pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. And similarly, when we do our next solution, we're doing sine of negative 1/2. So negative y values are down here in quadrant 4. So that means the missed solution is going to be in quadrant 3, because quadrant 3 also has negative y values. So we take a look down here, and we need the sine, so that means y values to be negative 1/2. So we have negative 1/2, which goes with 11 pi over 6. And we have 7 pi over 6, which also has the y value of negative 1/2. So the two solutions over here are x equals 7 pi over 6 plus 2 pi n, and x equals 11 pi over 6 plus 2 pi n. And that is the 4 infinite sets of solutions to that quadratic equation. All right. So I think you guys have been watching me do these for long enough. So I think it is time for you guys to try one. But before I turn you loose on your you try, we want to make some observations about this equation. So once again, this is a quadratic trigonometric polynomial. And it's quadratic in sign, so the substitution that may be helpful is to let y equal sine x. All right, so to resolve this u try, we're going to factor this. So we have 2y squared plus y minus 1 is equal to 0. And this factors into 2y minus 1 times y plus 1 is equal to 0. So then that gives us that y is equal to 1/2, or y is equal to negative 1. But y is sine x. So then we have sine x equals 1/2. And sine x is equal to negative 1. So then taking the inverse sine, we get x equals the inverse sine of 1/2, and we get x equals the inverse sine of negative 1. So then looking at our unit circle for the first equation, 1/2 is in quadrant 1, so the solution it's going to miss is going to be in quadrant 2. So that's going to be the upper half of our unit circle. So we find our y value of 1/2, and we get y equals 1/2 for pi over 6, and we also get y equals 1/2 at 5 pi over 6. So our two solutions are x equals pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. And then we look at our unit circle again, and this time we need the y value to be -1. But -1 only occurs once on the unit circle, and that's right on the axis in between quadrants 3 and quadrants 4. So this one's only going to give us one solution down here at -1. So it gives us x equals 3 pi over 2, but the range of the inverse sine function is between -pi over 2 and pi over 2. So our solution should be -pi over 2 plus 2 pi n. And it's worth noting, if you add -pi over 2 to 2 pi, you get 3 pi over 2, because those angles are indeed coterminal. Let's take a look at this next one. So this one asks us to solve, but this time it doesn't want us to get the infinite families of solutions. It says we only want to find the solutions for theta in between 0 and less than 2 pi. So we need to resolve this equation, and it looks almost exactly like, pardon me, the very first equation that we solved, which was 2 times the cosine of x equals -1. Well, it looks really similar. The only difference is instead of having only an x on the inside, it's got a whole bunch of stuff. But we're still going to do the same thing. So what undoes a cosine function? Well, the cosine inverse. So if we have the cosine of 2 theta minus pi over 2 is equal to -1, to undo the cosine, we're going to do the cosine inverse of both sides of the equation. And the cosine and the cosine inverse undo each other. And we're left with 2 theta minus pi over 2 is equal to the cosine inverse of -1. So we look at our unit circle. Cosine is x. So -1 occurs over here. And there's only one time when the x value is -1, and that's at pi, plus all of the coterminal angles. So our solution is going to be pi plus 2 pi n. We now need to solve this equation for theta. So the first thing I'm going to do is add pi over 2 and add pi over 2. So pi plus pi over 2 is going to give me, well, those cancel out, make this a fraction, so multiply the top and the bottom by 2. So that's 2 pi over 2 is the same as pi. So 2 pi plus pi gives me 3 pi over 2 plus 2 pi n. So now, finally, I need to get theta by itself. So I divide by 2, and divide by 2. So theta equals, make that a fraction over 1. So I get 3 pi over 2 times the reciprocal, which is 1/2. And then in the second one, the 2 and the 2 reduce. So then I get theta is equal to 3 pi over 4. Sorry, I wrote a second equal sign there, which is false. That was a plus. Plus pi n. And that is going to be our solution for all n in Z. So, looking back, we solved the same way we've been doing in the previous problem, but since theta wasn't already isolated, we had to manipulate the 2 pi n just like we would anything else. and we treated it just like a term. We combined our like terms, then divided, and that gave us our family of solutions for that trigonometric equation. And so we're like, yay, we're done. We pat ourselves on the back, but we're not quite done, right? So how is this problem different? Well, we only want the solutions where theta is in between 0 and 2 pi, right? So to help us visualize that, I'm going to factor my pi out, which would give me 3 over 4 plus n times pi. And I want this then to be between 0 and 2. So not equal to, though. So we can have our calculator help us out if we wish. So we go y equals, let's clear out what we have in here. And we have 3 over 4 plus x, and then we go second table. And we want all of the values between 0 and 2. So -1 doesn't work. We have 3/4, 7/4, 11/4 is going to be bigger than 2. So a fun trick that we can do with this, if you wanted some decimals, so we have 3 over 4 plus x. If you go alpha trace, choose y1, and then go math 2 and choose decimal. Now when you go table, it's going to show us both the fraction and the decimal representation in our calculator. And we want the values between 0 and 2. So then that means we're only going to want these solutions here and here. So we want n equals 0 and n equals 1. So if we put n equals 0 and n equals 1 in, that's going to give us theta equals 3 pi over 4 plus pi times 0, which is 3 pi over 4, and theta equals 3 pi over 4 plus pi times 1, which is going to give us, we see it right here, 7 pi over 4. And those would be the two solutions that we would want. All right, so let's keep going. So solve this equation, once again on the interval from 0 to 2 pi. But now this one, when we do a little comparing and contrasting, we notice that it is a mixture of both sines and cosines. So we must use identities. To write the trigonometric polynomial as the same trig function if possible. Or actually more generally as only one trigonometric function. And then I'm going to put if possible. because this is plan A. But sometimes we're going to have to do something else. But for us, this will be pretty much what we always do. So we look at this, and we have a sine, we have a cosine, we have a cosine. So it seems like we have more cosines than we have sines. So let's rewrite sine as cosine. The sine squared theta using the Pythagorean identity. And the Pythagorean identity, when solved for sine, is sine squared theta is equal to 1 minus cosine squared theta. So if we substitute that into the original equation, we get 1 minus cosine squared theta minus cosine squared theta equals 1 plus cosine theta. So now we collect up our like terms. So we have 1 minus 2 cosine squared theta equals 1 plus cosine theta. So now this is a trigonometric polynomial, so we need to move everything to one side. So we minus 1 and we minus cosine theta. Those cancel, and those cancel. So we get negative 2 cosine squared theta minus cosine theta is equal to 0. And then we're going to factor out our GCF, which is cosine theta. I'm going to factor out a negative cosine theta. And then that leaves behind a 2 cosine theta plus 1 is equal to 0. So now that I've got this factored, I have my two equations. So negative cosine theta equals 0, or 2 cosine theta plus 1 is equal to 0. So this, we divide by minus 1, divide by minus 1, we get cosine theta equals 0. Taking the inverse cosine, theta equals the inverse cosine of 0. And then over here we go minus 1, and we get 2 cosine theta equals negative 1, divide by 2, and we get cosine theta equals negative 1/2, or theta equals the inverse cosine of negative 1/2. So now we look at our unit circle, and cosine is x. So when on our unit circle is x equal to 0? Well, that's at pi over 2. And what's the other one where it's equal to 0? Oh, that's 3 pi over 2. So we get two solutions from this one. We get x equals pi over 2 plus 2 pi n. And we get x equals 3 pi over 2 plus 2 pi n. And then over here, we need to find when cosine equals negative 1/2. So cosine is x. X is negative in quadrants 2 and 3. So we have negative 1/2 here at 2 pi over 3 and at 4 pi over 3. So 2 pi over 3 and 4 pi over 3. then we were only looking for solutions between 0 and 2 pi. So our only solutions are going to be pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. Because if we add 2 pi, that'll make them bigger than 2 pi for all of the solutions. All right, so the next one is for you guys. So we want to go ahead and resolve try number 2. And before I turn you loose to work on this, we're going to need to use a trigonometric identity to resolve this. All right, so to resolve this try, the first thing we need to do is use the double angle identity here on this expression. So using our double angle identity, that is the same as the sine of 2 theta, which is equal to 1. So then we're going to take the inverse sine of both sides of the equation. So sine inverse and sine inverse. And so then the sine and the sine inverse reduce out, and we're left with 2 theta equals the sine inverse of negative or of positive 1. So then we want to take the sine inverse of positive 1. So sine is y, and we're only ever sine, or the y value equals 1 only once, and that's at the angle pi over 2. So we get pi divided by 2 plus all of the coterminal angles, 2 pi n. So then we finish solving for theta by dividing every term by 2, and we get theta equals pi divided by 4. Here the 2's cancel, pi n. And that is the family of all solutions to that equation. All right, so let's go ahead and look at the last example. I lied. I guess there's 2. So the penultimate example in this section, and then we'll do example 6. All right. So this time we wish to solve the equation 3 tan squared theta minus tan theta minus 1 equals 0. So if we let y equal tangent theta, we then get the equation 3 y squared minus y minus 1 is equal to 0. And then we want to solve this equation. If we try to factor this, we would need factors of negative 3 that add up to negative 1, but this only has factors 1 and 3. So it turns out that this polynomial is prime. So since it doesn't factor, we must use the quadratic formula. So it turns out you can do this always with any of these that are quadratic, not only if it's prime, just like with polynomial equations. We can always use the quadratic formula. So solving, we're going to get y is equal to negative b, so negative negative 1 plus or minus the square root of negative 1 squared minus 4 times a times c all divided by 2 times a. So negative 1 squared is 1. Negative 4 times 3 times negative 1. Negative and a negative make it positive, so we get positive 12. And then we have a minus minus out in front, so that becomes minus minus becomes a plus positive. So we end up with 1 plus or minus the square root of 13 all over 6. So then if y equals this, we get tangent theta equals 1 minus the square root of 13 over 6, or our other equation is the tangent of theta is equal to 1 plus the square root of 13 over 6. So then we need to solve each of these resulting equations. So then here we get theta is equal to the tangent inverse of 1 minus the square root of 13 over 6. And here we're going to get theta is equal to the tangent inverse of 1 plus the square root of 13 over 6. So then we've got to be a little bit careful because we have these, but then we need to get the wraparound. What was the period of the tangent function? So we know that sine and cosine both had period 2 pi, but the tangent function only has period pi, so it's plus pi n and plus pi n. And that would be our family of solutions to that equation. All right, so now we get to the last example. So example 6 is actually graphing calculator food. So it wants us to approximate the solution to the equation 4 times cosine 3x minus e to the x equals 1 on the interval 0 to infinity. So make that y1 on my calculator, and I'm going to make this y2 on my calculator. So I grab my graphing device, and I go to my y equals, and clear out what I have here. So I have 4 cosine 3x minus e to the x. And then my y2 is 1. Now I graph. And I was only concerned with 0 to infinity, so I'm going to change my graph in a second. Oh, my window's all messed up anyway from what I did before. So let's go window. Let's make our x min 0, make our x max 20, leave our x scale at 1. Let's make our y min 0, make our y max 2, and we can leave our x scale at 0.1. And we press graph. And we see, after it graphs, we only have the one intersection point. So to find it, we go second, calculate, 5 for intersect, first curve, second curve, guess. And our calculator grabs the solution for us. So we have one intersection. And that would be our solution, is the x value right here. So we can always use the intersect method to solve equations.